Welcome back to the deep dive. We're continuing our journey through the online encyclopedia of integer sequences, the OEIS. It's just this incredible resource.
It really is a goldmine for number theory fans.
Today, we're tackling a specific sequence, A000287.
Yes, A000287. This one counts rooted polyhedral graphs within edges.
Okay, rooted polyhedral graphs. Sounds technical.
It does a bit, but think of it like counting the different ways you can make the basic skeleton of a 3D shape, like a cube, but with a specific starting edge marked. It's a neat little corner of combinatorics.
Combinatorics, right? The maths of counting things.
Exactly. And this sequence shows some really beautiful mathematical connections.
So our mission today, unpack what rooted polyhedral graph actually means, look at some maybe surprising features, and then explore the tools mathematicians use to, define and understand it. Should be fun.
Absolutely. Expect a few aha moments.
Okay, let's start there then. Rooted polyhedral graphs. What are we really picturing, and how do you even start counting them? Seems complicated.
Right. So imagine a convex polyhedron, like a standard cube or maybe a dodecahedron, those shapes with flat faces and straight edges.
Got it. Like dice shapes.
Precisely. The polyhedral graph is just its wireframe, the vertices, the corners, and the edges connecting them.
Okay, the skeleton.
Exactly. Now, the rooted part just means we've singled out something specific. We pick one edge, or maybe a vertex, or even a face, as a kind of anchor, a starting point.
Ah, so that makes shapes that look the same potentially count as different if the root is different.
That's the key idea. It standardizes the counting. And this isn't a new idea. There's a lot of history here. People like W.T. Tett did some really foundational work, significantly advancing how we think about these graph structures.
Right. So the sequence itself,
Yeah.
It starts at 6 is 1, then 7 is 0. Wait, 0?
Yes, A70. It's impossible to make such a graph with exactly 7 edges.
Interesting. Then it jumps to 84, 896, and it grows fast from there. It's definitely not obvious how you get those numbers just by looking.
No, not at all. The pattern isn't immediately clear, which makes the underlying mathematics even more intriguing.
So let's get into some of those intriguing properties. I saw a comment in the OEIS entry from Louis Chen pointing out something odd.
Ah, you mean the parity pattern.
Yeah, it says AN appears to be odd if and only if n equals 2k2 for some integer k equals 3.
Yes, that's a fascinating observation.
So hold on. We're counting these quite complex 3D-ish structures, and out pops this simple rule about odd or even counts linked just to powers of 2 minus 2. That seems wild.
It is pretty remarkable, isn't it? It's exactly the kind of hidden regularity mathematicians love to find. We have this complex combinatorial setup, and suddenly a simple arithmetic condition, the parity, reveals this structure related to powers of 2.
What does that usually hint at when something like that appears?
Often it suggests deeper algebraic structures or symmetries underlying the counting problem. It tells you there's more going on than just brute force enumeration. And speaking of what's going on, the growth rate. These numbers don't just climb, they explode.
Explode. How fast?
Very fast. There's an asymptotic approximation worked out by Vaclav-Kochesovek. It shows that for large n behaves roughly like, let me get this right, 2n plus 1 divided by 35 squirt n 52.
Whoa, okay, so exponential growth, that 2n part is huge.
That's it.
But pi, square root of pi, in counting graphs.
Yes, isn't that wonderful?
Certainly surprising. How does pi get involved in counting discrete objects?
It's a common theme, actually, in asymptotics for combinatorial objects. When you're looking at the behavior for very large n, these constants from continuous mathematics, like pi and e, often emerge. It usually comes from using tools like generating functions and complex analysis, like saddle point methods to estimate the coefficients. It shows this deep link between discrete counts and continuous analysis.
Yeah, okay, that makes a bit more sense. So we have this odd even pattern, this explosive growth involving pi.
Yeah.
How do mathematicians actually calculate these numbers? Or, define the sequence rigorously?
Right. Well, that's another beautiful aspect. This sequence, A000287, is a great example of how you can approach the same mathematical object from multiple angles using different tools.
Different tools? Like what?
Well, for one, there are explicit recursive formulas. Simon Plouffe provided one, for instance, that lets you calculate an if you know the values for smaller n, specifically going back to an4.
Okay, so you can compute it step by step if you have the earlier terms. That's useful.
Very useful for computation, yes. But then they're also generating functions.
Ah, the magic series were the coefficients or the sequence terms.
Exactly. It's a way to package the entire infinite sequence into a single function, usually a power series. And once you have that function, you can study it. You can find differential equations that the generating function satisfies, as Gershon documented for this sequence.
So you turn the sequence problem into an equation problem.
Precisely. And sometimes solving that equation or analyzing its properties tells you things about the sequence, like the asymptotic growth we just talked about.
So it's like you have these different mathematical perspectives. The recurrence tells you how to build it step by step, the generating function gives you the whole picture as one object, and the asymptotic formula tells you what it looks like way out on the horizon.
You've got it exactly. It really highlights how mathematics isn't monolithic. Different tools give different kinds of insights. It's a very collaborative too. One person finds a recurrence, another finds the generating function, someone else figures out the asymptotics.
It builds a richer picture.
A much richer picture, yes.
So today we've taken this quick look into OEIS A000287, the number of rooted polyhedral graphs with inné edges. We saw its slightly strange starting values, that surprising odd-even rule, its incredibly rapid growth, and this whole network of descriptions, recurrences, generating functions, differential equations.
It really demonstrates how even one sequence in the OEIS can open doors to some pretty deep and interconnected mathematical ideas. It makes you appreciate how these different mathematical languages, recurrence relations, generating functions, analysis, all converge to describe the same thing.
It definitely does.
And it leaves you wondering, doesn't it? If one sequence like this holds so much interesting structure, how many other sequences in the OEIS have equally fascinating stories just waiting for us to fully uncover them? What other surprising connections and mathematical insights are hidden in there?